It's great. Like my.
Once he does the worst, that's not twice. Wow.
Yeah, I think all this could be. Well.
Okay, page 6. Did we do the graph together yesterday?
Yeah.
Number 8, we did. Okay,
We did the first one.
okay, let's do number 9. So we can kind of get that full practice. Again, what's new about this graph that we didn't see on the quiz is just ones involving negative and positive infinity. So that just means that as the arrows exit the graph, where's the graph headed? Is it along the, if it's a number, that means it's flattening out along that horizontal asymptotes. Try number 9. And then I have a key attached where you can see you're on the right track. Now, again, graphs may be different because of interpretation, but page 6. If you get done with page 6, if you get done with that problem, then next thing we're going to do is page 11. So go to page 11 if you feel like you're good and ready to go. But I'll go over this after you guys try it. So part A, approaching negative infinity. That means that I'm following the arrow off the grid towards the left, and I want that y value to be hovering close to 8. So as it exits the graph, I just want it to flatten out and show that it's holding and getting close to that y value of 8. Part B is just the order pair. Part C, limit doesn't exist. A lot of options that you can do here for part C. You can, I purposely made it a non-removable discontinuity, but you could have made an endpoint. You could have made it an asymptote. And so it doesn't have to look like mine for part C. Part D, approaching 1 from the left side of 1 is equal to 3. So yeah, 3. So whenever I see a limit problem, I always just like to put a hole there, just because that feels the safer way to go, especially so that I don't accidentally conflict with another point. And if I need to fill that in, something else will tell me to fill it in. I don't have to worry about it. So I always like to put close open circle, so I don't have to erase. Approaching 1 from the right side of 1 is equal to -4, so I know that from the other side of 1, I want to move towards -4. Limit as x approaches 3 equals positive infinity. I want a vertical asymptote, but I need to make sure that I need both branches to head towards positive infinity. Part G, limit as x approaches positive infinity, it's going to hover right around -4. So it's going to flatten out around -4. Yes.
Like line.
You don't have to. I mean, if I can tell that it's a flat line, then that's good enough. But I did a dotted line is just to kind of show that if my graph is headed off the grid, then that dotted line helps me see where that is. They don't have to do that. Okay, let's go to page 11. Actually, before we go to page 11, let me just do a quick review on page 9. Okay. So again, big picture here. Whenever you're dealing with limit approaching a real number, with approaching 3, approaching 0, approaching 5, it doesn't matter if there's a one-sided limit. You're just always going to plug in that x value. Right? Ignore the one-sided limit, plug in the x value. And there's 3 categories. You're either going to get a real number. If you get a real number, you stop. There's nothing more to do. No decimals involved. If you plug in, if you get a 0 over 0, then again, no decimals, but you know it's going to be one of the factoring problems, either factoring, reducing, something. You know there's a hole. You're just trying to remove the hole, just like how you did on the quiz, but again, no decimals at all. You're just ignoring the one-sided limit, and you're just dealing with the real limit. Now, if you get a 10 over 0, 8 over 0, 9 over 0, then you know there's a vertical asymptote. And then if it's still a one-sided limit, then you know that you're going to test between decimals between 2.9 or 3.1. That's the only time you do decimals if you realize there's a vertical asymptote. Okay. Now, if it's limit approaching positive or negative infinity, we completely switch gears. We don't plug anything in. We go directly to finding the highest degrees in the numerator and denominator. If the denominator has a higher degree than the numerator, then your limit is always 0. If your numerator and denominator have the same degree, then you just take the ratio of the coefficients. If your numerator is higher than your denominator degree, there is no limit, but you're having to choose between plus or minus infinity, and this is where you got to do an additional test. You got to either test 100 or test -100. Make sure that you know continuity conditions. We've been doing a lot of problems, so hopefully you guys are feeling comfortable with each of those conditions and applying them and writing out exactly those statements. And IVT, we'll do some IVT problems later as well. Okay, so let's go to page 11. Okay, so start number 1, A through E. Go ahead and try those first. The key is on the back. You can check your answer, but I will go over each with you once you've had a chance to try. Okay, part A, we insert -4 into the expression, no decimals at all. We're just wanted to know what's going on here. So -4 into the expression, we get -7/0. So that allows us to visualize what's going on. We know there's a vertical asymptote. The limit doesn't exist. That would normally be our answer, but we got to do something special now that we realize there's an asymptote and it's only asking about the behavior from the left side of the asymptote. So we got to choose a decimal value to help us decide between these two options. So slightly to the left of -4 is -4.1. Insert -4.1 in for x. We get negative over a positive, therefore negative infinity. So notice that we only deal with decimals if we first realize that there is an asymptote to work with. If there is no asymptote, you're going to go through the entire problem without touching any decimals. Okay, try part B. For the vertical asymptote. Yeah, it's my 3 to the 0, it's not for x, or it's a break on 3. So there is a break at graph. But is that break going to interrupt? Yeah, so let's say, so our function is
So if it was like, if it was like just 2 or like 3, I guess.
if
No, no,
it's like
3.
x minus 5, then that'll be an issue.
Okay.
And we would stop the problem, say it's a function not continuous, every t goes in the 5.
Okay, part B, limit as x approaches -infinity. We don't plug any numbers in. We go directly to comparing our degrees. Our degrees match. So it's just the ratio of the coefficients, -1 over +1, which is -1. Part C, limit as x approaches -4 from the right side of -4. We don't care about that notation there. We just want to start with -4. So -4 into the expression. We get -16 over -2, which is 8. That's a real number, and we stop. There's nothing more to do. And we don't want to be thrown off by that one-side limit. Sometimes students feel like they got to do something special and they start playing with decimals too early, and that throws off the answer, right? So we only do any decimals if there's a vertical asymptote. Here, there is no vertical asymptote. The limit exists. So if the full limit exists, then the one-side limit will be the same as that full limit. Okay, part D. We don't want to get thrown off by the order pair, right? The order pair is giving us a value. But in order for a limit to exist, we have to see if, especially if a function is split on either side of -4, which it is, the y values are not in agreement. Therefore, the limit doesn't exist. Part E, we see infinity again. This time, the degrees do not match. The numerator has a higher degree, which means that there is no limit, but we're choosing between these two options. We got to test the number. So we'll test x equals 100. Get a negative over a positive, which is negative infinity. Any questions A through E? Guys, let me extend this with a part F. Let me hold on a second. Let me write this down. Okay, so just write this down somewhere on your paper. Limit as x approaches negative infinity, 2x squared over 3x minus 2 squared. So we're approaching positive or negative infinity. So what's our strategy? Okay, look at the degrees, right? What's the degree of the numerator?
2.
2. What's the degree of the denominator? Also 2. We don't want to be thrown off by the fact that we only see an x there, but it's really a degree 2. And my suggestion is we really want to FOIL this out, right? Because right now something is still hidden from us. We know we got to take the ratio of the coefficients, but what's the true coefficient of the denominator? Is it a 3?
It's a 9.
It's a 9, right? We have to FOIL this out. Now, the other terms are not that important. We just have to make sure that we get that first term spelled out. Otherwise, we're not going to get a good reading on that coefficient. So 9x squared. These numbers are not that important. It's the 9 that we really want to make sure we get. And the limit is just 2 over 9. We don't want to let that negative infinity throw us off. We don't change the sign. It's only 1. It's just the ratio. The sign has no impact. Okay, whatever that ratio is, we keep it. Okay, don't change the sign. So if you see limit approaching infinity and you see an opportunity to FOIL, go ahead and FOIL everything out so everything is clear. Otherwise, it's easy to look at this problem and make the mistake that the numerator has a higher degree, which it doesn't, or recognizing that the degrees are the same, but forgetting to expand this out. And so some students write 2/3 as a limit, when it's really 2/9. Or changing the sign and getting the right answer, but then adjusting it incorrectly and making it negative 2/9. Any questions there? Okay, part B. Step through continuity conditions. At x equals -4, so we start off with the order pair. Limit as x approaches -4 from the left and from the right. We already saw from C and D that they're not the same. Therefore, we already concluded that the limit doesn't exist. Okay, so what type of, can we stop and determine what type of discontinuity?
Non-removable.
Non-removable. Okay, part C. Oh, sorry, number 2. Okay, find the horizontal asymptotes. Okay. So we know it's going to be involving limit as x approaches infinity. Right. is horizontal asymptotes is when we look at the end behavior. So what do you notice? Same degree, so therefore, what's the ratio of the coefficients?
-1/4.
-1 over, careful though,
Oh, yeah.
square root of 4, which is -1/2. Now, that's one of the asymptotes. Is there another one? Yes. That's what,
Positive.
positive 1/2. So if I'm asking for horizontal asymptotes, make sure that we create equations for them. So we have to say y equals 1/2, y equals -1/2. Or you can say y is equal to plus or minus 1/2. But make sure you include y in your equation. If you just say 1/2 and -1/2, those are not equations of lines. We have to say y. Any questions? Yeah.
Where is the positive for that?
Okay, where's the plus 1/2 come from? So, yeah, I know you're probably absent on that day, but we talked about how these graphs are kind of strange. They have split asymptotes. Like this. Anytime that there's a square root in the denominator, the graph is going to look strange like this. So, but one side will be the ratio that you see, but if I'm going in the other direction, it's going to be the negative version of that ratio. So whenever you see this type of problems, just understand that you have two horizontal asymptotes, but they're just plus and minus of the same ratio.
All right.
Okay, number 3, show whether IVT applies. So with IVT, we have to consider that what our goal is. Our goal is to see, can we reach that y value of 2 using just limited amount of information. So the first thing is we have to decide, is there a continuity issue in our interval? So this is not a polynomial, so we can't just have a blanket statement and say that it's continuous everywhere. Is there a potential continuity issue in this function? So if there, where do we look for any potential breaks in the graph? Denominator, right? So if we set the denominator equal to 0, in this case, that's going to allow us to look for vertical asymptotes. So where's the vertical asymptote for this function?
+3.
+3. Now, it doesn't mean that we automatically fail IVT if there's a vertical asymptote, but we have to see, is this disruption going to impact my interval? It's not, right? So there's only one disruption, and that disruption is outside the interval. So our interval will be uninterrupted, and our function is continuous on that closed interval. So we go ahead and make that statement. Okay, so that's out of the way. We have to first establish function is continuous. And now we want to guarantee this target y value of 2. So how can we use the endpoints to help us determine that? Yeah, find the y values at these endpoints, right? And we want one y value to be where? Less than 2, and the other y value to be higher than 2, right? That's what we want. We're trying to decide what is the minimum amount of information without looking at the graph for us to guarantee that y value 2. So I need continuity, and I need one endpoint to be below, one endpoint to be above. And that's the least amount of information that will allow me to guarantee what I'm looking for. So I'll plug in f of 4 first. The 4 into the function. So I have 4, which is a value above 2. Yes.
How do you know it's continuous?
So we know this vertical asymptote, right? There's a break at 3. But is that 3 going to affect my interval? Right. So if it's outside the interval, then we're safe. We can say continuous. But if this disrupts the interval, then we have to stop and say function is not continuous. IVT does not apply. Okay, so f of 8 We have a y value above 2. Now we're hoping to find a y value below 2. Eight over 5. So 8 over 5 is less than 2 because we know 10 over 5 is 2. So 8 over 5 is less than 2. So we're safe, right? We have a value above 2 and a value below 2. So we can state our statement. So f of 8 is producing 8/5, which is lower than our target. And then our target is less than my other endpoint. Okay, so I proved IVT. I know that this y value is going to live somewhere on that interval. But there's one more thing that I'm looking for here. It says find the what? C, which is really the x value. So if I know what my target y value is, how can I find the x? Yeah, replace the 2 in for the y and solve for x. Cross multiply to get rid of the fraction. That x value should land nicely between 4 and 8, and it does. So that should confirm we're guaranteed at this point we shouldn't be getting a c value that's outside the interval. Okay, number 4, see if you can fill in A through E. That should be good. That should go pretty quickly. Any questions with this review sheet? Okay. Let me review comparative growth rates. That's we did this closer to the end of our notes. The idea here is that if I have a numerator and denominator, and if its limit approaching infinity, if I have predictable functions above and below each other, then my limit is pretty quick. I can either decide that the limit is 0 or decide that it's going to either plus or minus infinity. And the reason that we're able to make such a quick conclusion is only if they fall under these nice categories. So logs, radicals, polynomials, and exponentials. These are functions that we're going to use the most often in our course. L is for logs, R is for radicals, P is for polynomial, and E is for exponential. So here's the idea. The idea is that if I have limit as x approaches infinity, and if I have a slower function over a faster function, what's my limit going to be? 0, right? If the denominator is growing faster than the numerator, then that fraction value is getting smaller and smaller and smaller. And then likewise, if I have a limit as x approaches infinity of my function, which the faster is above my denominator, then
Infinity.
yeah, it's either what? Positive or negative infinity, and then we got to test x equal to 100. Okay, so does that make sense? Okay, so let me do 2 quick examples and have you guys try it and see if you're comfortable with this topic. Okay, try those.
Like a log over a log.
No, yeah, if that's the case, we have a way to deal with that later on in the course, but right now, yeah, it'll be nice and easy and clean cut. Okay, so which category is the numerator? Denominator is which side is growing faster? Numerator, radical. So we know we're choosing between these 2 options. We got a test, so we'll test 100. So if we test 100, numerator is negative, denominator is positive, so negative over a positive is negative.
On the test, are we gonna be given that log, like the, or do we have to memorize?
Yeah, you gotta memorize this. Yeah. Okay, number 2, what category is above? Polynomial. Denominator is exponential. Which side is growing faster? Denominator, therefore limit is 0. Okay, let me pick out some more problems for us to practice with. Yeah, why don't we do page 17 and 18? And then the keys are on the following pages, 19 and 20. So just use the space on the right to show your work. And just continually just check back and forth and see how you do. I'll come around, see if you guys have any questions. And then So page 17 and 18. One value close.
Oh, close.
Close. Closest to one. You know, if you're stuck or something doesn't quite make sense. Right. For efficiency, for efficiency, we have two different drafts of the same thing. Got that information. You can just see. I said it's supposed to be 1/6, they're not. Now, it feels kind of negative for it, we use the limit in ID2, but it's their stitch structure on this side. So, yeah, so I look for my, where's X, where's -4, defined? Not here, it's less than, and this one, less than or equal to.
Plug in there.
Yeah.
Okay.
Because I need to know whether my. Because otherwise, you know, just why it's like. Any questions on page 17? Any questions on 17? So page 18 is just practicing stepping through continuity conditions and being comfortable with using that to help you solve or to determine what type of discontinuity it is. On page 18, if you like, number 3, you can write it using 3 parts, right? You can have this be less than -1 and this be greater than -1. More than welcome to write it that way before you delve into each of the conditions. But just understand that if you see this on the test, it's always going to be written out this way. You'll never see anything written out this way. If you want it written out this way, you got to create it. Thanks. Okay, a few more things here. I will have a help session this afternoon. I have a meeting from 3:30 to 4, so if you stick around, 4 to 4:30, I'll do a help session. And then tomorrow morning, 7:15, I will go over, that last test review worksheet in your packet, which is page 21, to 22. But you're more than welcome to, go through it earlier. And then also, look at, page 25. Right, these are all the test topics, so make sure that, you're comfortable with all of them. Look through your, notes, look through your quizzes, right? So, there are problems involving conjugate, common denominator. Make sure you're still comfortable with those. And, but if you feel good about the review we've been doing the last few days, you should feel good about tomorrow. No calculator. When you guys come in tomorrow, you put your phones up, you're gonna put your foot back in the front, okay? And then, I'm gonna start handing out the test. I'll give you guys as much test as I can. So as soon as you walk through the door, there'll be a test on your desk, and you can start the test as soon as you sit down, okay? Okay, all right, go ahead and get your phones.
Be a long test, or do you just want to like get started?
It's 3 pages.
Okay.
I just want to give you guys some time.
Makes sense, thank you.
So if we want to attend the help session tomorrow, do we just come in person at 7:15 or like?
Yeah, 17, I will also send out a Tues link.
Okay, so you can just join virtually.
Yeah. Oh, and then for tomorrow's morning, help session, I will send out a Teams link through Remind. So if you're at home and you want to take part,
Is there gonna be a team link to the one?
yes. No, it's too short, but tomorrow I will.
Person too, right?
Yeah, it's in person and virtual, but I'll record it as well if you missed it and you want to watch it over. But I did record this, tomorrow's, review worksheet already on my website, so if you want to watch that one, you can watch that one too. So this, you may want to rewrite it to help you see a little better. Maybe if you write it this way, it feels more comfortable, right? Because then you have the order pair. You want to find a limit, but it's the same function on either side of -1, so just the limit of,
Do I plug in -1 to X?
yeah, plug it in one for X.
Does do you get 0 over there?
Yep. There's a whole, right? So you got to factor, reduce, reevaluate, which means that the limit does exist.
When you get 0 over 0, that's when you know you have to do.
Yeah.
Yeah,
If you get 0, 0, you know that there's a real number waiting for you at the end.
but then what would it be? We're limited in last two.
Oh, sorry, sorry. It's like -1, which is -2. That's enough. Yeah, they don't agree.
Wait, why is it not?
It's removable. Non-removal would be if the second edition fails.
Oh, there's no limit at all.
Right, there's no limit.
Okay.
Everything got safe success.
Thank you.
Tomorrow, thanks.